So welcome to this session. So till now we discussed about the basic parameters of our transmission line, transmission line equations, transmission line primary parameters, secondary constants, and different impedances like input impedance, characteristic impedance, and load impedance. Using those parameters, we derived a few equations like input impedance of the transmission line, and we defined voltage standing wave ratio, reflection coefficient, etc. And we have observed different transmission line parameters also. Now, how to relate the powers which are traveling from a transmission line, how to relate the waves which are traveling in a transmission line when a junction is formed. That's what we are going to discuss in this session. And along with that one, we will discuss one more topic as impedance matching. How it will be useful for impedance matching in any transmission line circuitry. That we will discuss in this session. Initially, we will start the session with scattering parameters. They are the parameters which are useful for relate the powers which are in our transmission line junction. Now, whenever we are considering a circuitry, here circuitry means it's not consisting of any transistors and resistors, that it consists of a few transmission lines. That whenever any such junction occurs in the transmission lines, how to relate the powers which are traveling in our junction, that can be possible with our scattering parameters. Now we will observe the scattering parameters. In short, they are also called as S parameters. For understanding the scattering parameters, we are supposed to assume that there is a junction in the transmission line circuit. That if whenever there is a junction, definitely as we said, that some ports will be there. Now imagine a junction is there in our transmission line circuit like this. This is the junction that we have. For this particular junction, you may have one input port and different output ports. Let us take, this is one of the output ports that what we have. This is another output port. Similarly, you may have another output port like this. So for our convenience, I am assuming that for a particular junction, you have only one input port and remaining all are output ports. But you can take any one of these as input ports and this one as output port, no problem. Right? Now let us take, this is the ith port that what we are considering. This is the first port, second port, up to this is nth port. So this is a junction which consists of n ports. Right? Now, once again, for our convenience, I will consider the generator is connected to the ith port. That's the whcih is connected to the ith port, and the output may be observed at first port, second port, up to nth port. Right? So what I do is just I will assume few parameters like this. So whenever we are considering a port, the wave which is applied to the ith port as a suffix I. This is a universal notation that what we are supposed to follow for scattering parameters, that the voltage or the wave which is traveling to the port is AI, and the wave which is reflected or scattered, that's why it is called as a scattering parameter. The wave which is scattered from the same port is BI. That's what we have here. Similarly, let us take the wave which is applied to the first port is A1 and scattered from the first port is B1, right? And applied to the second port is A2, scattered from the second port is B2. Clearly remember the directions also. Here what I am saying is this is scattered, just it is moving away from the port. It is moving towards the port. Similarly for the nth port, what you will have is AN as the input that what we are applying to the nth port, and BN is the scattered output or the scattered wave which is observed at the nth port. Right? Like this, what we have is different parameters, that's there are input waves and output waves that what we are observing at ith port and up to nth port. Now a very simple equation will be there. Whenever we are observing the reflection or the output which is coming from the ith port, you are also supposed to consider all the reflections which are coming from first port to the nth port. When you will get reflection, whenever the load which is connected here, let us take ZL1 is not equals to the Z0, characteristic impedance of our junction, then definitely some reflection will be there. Here also, if ZL2 is not equals to Z0, reflection will be there. ZLN is not equals to Z0, definitely reflection will be there. That the load which is connected at the end of our ports is not equals to the characteristic impedance, this reflection will be considered for the calculation of our BI. So a simple linear equation can be written for like this: BI is equals to B1 plus B2 up to plus BN. n. That is, the reflection which is observed at the ith port is a summation of all the reflections which are coming towards the junction from B1, B2 up to Bn. Now what is B1? What is B2? Just observe. B1 is the reflection which is coming from that port, which is equals to the input into some coefficient. That is nothing but the reflection coefficient that what we have, right? That can be written as B1 is equals to SI1. That the coefficient that what I am defining is SI1. Now here clearly examine this SI1, that is the coefficient that what I am defining. SI1 is nothing but a coefficient which is observed when the input is applied at ith port, output is observed at first port, multiplied with our input wave or the applied wave A1. Plus similarly, how you can write this B2? SI2 A2 up to this can be written as Bn multiplied with SIn or SIn into Bn, whatever it may be. So here clearly the reflection at the particular port Bi can be written as SI1 A1 plus SI2 A2, this is nothing but B2 up to SIn Bn. Now you have to generalize this particular equation for different applications. Now what you have to do is just you have to generalize this equation, that by substituting I is equals to 1 to n, if you are generalizing the equation, what you will get here? B1 is equals to S11 A1 plus S12 A2 and so on plus S1n an. Just what I am doing is I am generalizing this equation by substituting I equals to 1 to n. Similarly, B2 is equals to S21 A1 plus S22 A2 plus and so on plus S2n an. Similarly, if I is equals to n, then Bn is equals to Sn1 A1 plus Sn2 A2 and so on plus Snn an. Now just observe these equations, all they are just linear equations which are in terms of B1 A1 A2 up to An, B2 A1 A2 up to An, like that. You can easily convert all these equations into a matrix form. Just take these n equations and write down them as a matrix, then you will get a beautiful form like this. Now the equation which is compiled after observing all these, the matrix form which is compiled after observing all these equations is B1 B2 up to Bn, which is equals to, since it is a linear equation, easily you can write down this one, S11 S12 up to S1n, S21 S22 up to S2n. Similarly, this last one is N1 Sn2 up to Snn and multiplied with the coefficients A1 A2 up to An. Just you observe this equation, this particular form, the output powers or the scattered powers or the reflected powers, whatever it may be, that they are represented as B1 B2 up to Bn is equals to some matrix which is the coefficients obtained from either reflection or transmission. Later we will observe which one is reflected or which one is transmitted. Okay, so coefficients multiplied with the input waves or the input voltages. That's what you can say. Clearly remember, they are not the powers. A1 A2 up to An are not powers, they are waves. Waves means just voltages. Here also B1 up to Bn is just simply waves. So in short form, this can be written as B, which is equals to S into A. Now what is B is equals to S into A? Clearly this is a matrix which consists of all reflected or scattered outputs. That's what you can say simply. Similarly, S stands for S parameters. What is S parameters? Scattering parameters. Using this one only, you can clearly observe how much amount of power will be scattered. Now, A is nothing but simply input or applied waves. So, the output is equals to scattering matrix. This matrix is said to be the scattering matrix. Scattering matrix into input. So, this is a very simple relation. Now, we will observe for a simple network, a two-port network, how this can be interpreted and what are different parameters we have for that particular port. Now we will observe as an example. Now consider a simple two-port network. So how a two-port network will be? Let's take this is a two-port network which consists of just two ports, right? Let us assume the wave which is applied to this port 1 is A1. That's what you are supposed to consider. And what is the wave which is applied to the port 2? A2. And here the reflection or the scattering wave which is coming from port 1 is B1 and the scattered wave which is coming from port 2 is B2. Now this can be characterized with a matrix called as scattering matrix. You can connect this source or the generator at port 1 or port 2, no problem. If you are applying the source at port 1, A1 will exist. If you are applying source at port 2, A2 will exist. If you are observing the reflection from port 2, you are naming that one as B2. If you are observing reflection or the scattering wave from port 1, you are naming that one as B1. Now write down those general equations for our two-port network. If you are writing those equations, what you will get here? B1 is equals to S11 A1 plus S12 A2. Only two ports are there, right? Similarly, second port B2 is equals to S21 A1 plus S22 A2. Now with the help of these two equations, we can correlate the input waves and the output waves are the scattered waves, and we can interpret them, what they are, right? One by one, we will try to interpret what is S11, S12, S21 and S22, right? It is very easy to remember also. Just what you do is you remember these two equations. Don't go for the interpretation of S11. Don't remember them. Interpret them. Okay. One by one, what I do is just I'll give you what these four coefficients. Now start with S11. Now what is S11? S11 is equals to, for S11, just you close this one. Then you can observe it is B1 by A1. Simply it is a ratio of B1 to the A1. So S11 is equals to B1 by A1. If you are closing means you are making this A2 to 0. Provided A2 is equals to 0. That we are not applying any input at the second port. And we are observing this particular coefficient S11 which is equals to B1 by A1 at A2 is equals to 0. What is the meaning of this one? B1 reflected from port 1. A1 incident at port 1. Right? Here clearly it is the reflected power to the incident power. Reflected power to the incident power is always called as reflection coefficient. So this S11 can be interpreted as reflection coefficient at port 1, right? So here clearly you are observing this is at port 1 and it is a ratio of reflected wave to the incident wave. That's why it is called as reflection coefficient at port 1. Similarly, I want S12. Now consider S12. S12 is equals to obtain this S12, just you close this one. Then you will get B1 A2. So it is the ratio of B1 to the A2, B1 by A2. Provided A1 is equals to 0. Right? A1 is equals to 0 means you are not applying any input at the first port. Without any input at the first port, you are observing this particular quantity S12, that is B1 by A2 at A1 is equals to 0. What is B1 by A2? A2 is in this direction, just it is entering this junction and it is leaving the junction. Here it is not reflecting, it is scattered as output. Right? Whenever the input is applied at port 2, it will be scattered to the port 1. So this is called as transmission coefficient. It is transmitting from port 2 to port 1. Right? It is not reflecting, it is transmitting. That's why the ratio of B1 by A2 at A1 is equals to 0 is always called as transmission coefficient. This is not reflection coefficient. Simply it is transmission coefficient from, it is not yet, from port 2 to 1. So here clearly the wave is transmitting from A2, so the A2 means port 2 to port 1. That's what is called as a transmission coefficient from port 2 to port 1. Similarly, you can examine the second equation also. We'll examine that one. Now come to the second equation. In the second equation, you can observe S21 initially. So S21 is equals to, for this S21, just you close this one. What you will get is B2 by A1 yet A2 is equals to 0. So simply it is B2 by A1 yet A2 is equals to 0. What do you mean by B2 by A1? That B2 is observed at port 2, A1 is applied at port 1. So whenever the input is applied at port 1, how much amount of wave is transmitted to the port 2 we are observing here? that is B2 by A1 at A2 is equals to 0. So here clearly this is also a transmission coefficient. So applied at port 1, observed at port 2. So this is simply a transmission coefficient from which port to which port? From 1 to 2. Now just observe S22. S22 is equals to S22 equals to, just to close this one, then what you will get here is B2 by A2, B2 by A2 yet A1 is equals to 0. What do you mean by B2 by A2? B2 is the scattered power at port 2, right? A2 is the applied power at port 2. So the reflected power to the applied power, it's once again reflection coefficient. So this can be taken as the reflection coefficient yet port 2. So here if you are considering a simple 2-port network, S11, S12, S21 and S22. So these 4 are 4 different coefficients. S11 and S22 are the reflection coefficients. S11 reflection coefficient at port 1, S22 reflection coefficient at port 2. S12 and S21, these 2 are transmission coefficients. One is from 2 to 1, another one is from 1 to 2. Like that, we have 4 parameters. If you are increasing the number of ports, that is if a 3-port network is taken, you can analyze the same, that how the voltage distribution or how the wave distribution will be there among all those ports can be obtained using this simple analysis. That's why the scattering parameters or the scattering coefficients or the simply S parameters are very important in analysis of our transmission line junctions. Not only transmission line junctions, you can use that one for microwave junctions also. Whenever a microwave junction is taken, it's how the power will be distributed. So actually they are not meant for power, they are meant for voltage, but the same analysis can be applied for power also. So how the power will be divided or distributed among all those ports can be analyzed using our scattering parameters, and this is a simple derivation and analysis of our scattering parameters. Now you are supposed to remember what are the properties of scattering parameters. Now we will observe what are different parameters of our scattering matrix. But as you observed how to formulate our scattering matrix, just we will observe what are different properties, right? Not parameters, different properties of our scattering matrix. First you observe what is the type of our scattering matrix. Scattering matrix is always a square matrix with order n by n. So whenever you are representing the scattering matrix, clearly remember that the order is n by n. What is n here? Number of ports. That how many number of ports in a particular junction you are supposed to calculate, then the scattering matrix is of order n by n. As an example, if you are taking a 3-port device, then it is simply 3 by 3. If you are considering a 4-port device, it's it is a 4 by 4 matrix. I'll give you an example. We will have one simple device called as Magic T in our microwave devices. That Magic T will consist of 4 ports. That E-plane T will have 3 ports and one more port will be there apart from that one. So it's a 4-port device. For those 4 ports, if you want to derive the scattering matrix, then you have to use a 4 by 4 matrix. And a circulator will be there, a 3-port circulator will be there. Then you have to go for a 3 by 3 matrix. A 4-port directional coupler will be there. For a directional coupler, 4 ports will be there. For that, you have to use a 4 by 4 scattering matrix. Like that, purely depend upon the type of device what you are considering, and depend upon the junction, that's a unity count, how many ports, and based on that one, the scattering matrix order will be decided. And for a reciprocal junction or a reciprocal device, always it is a symmetric matrix. Symmetric matrix means Sij is equals to Sji. This is clearly, remember that this is only for a reciprocal device. If it is non-reciprocal device like circulator, isolator, gyrator, all these are some microwave devices, and so this property is not applicable. Right? Whenever the junction is a reciprocal junction, then it is a symmetric matrix. Sij is equals to Sji. Now, the third property is all the reflection coefficients for a perfectly matched junction are 0. Now, what are the reflection coefficients you observed in our previous property? S11 is reflection coefficient, S22 is reflection coefficient. Similarly, Snn is also reflection coefficient. So, all the reflection coefficients for a perfectly matched junction, since it is a perfectly matched, obviously there will be no reflection. So, the reflection coefficients are 0. That simply you can say that Sii is equals to 0 for a perfectly matched junction. And the next property is it is always a unitary matrix. Always unitary matrix means S into that the scattering matrix S into its complex conjugate S star is equals to, it's the identity matrix I. So simply it is a unitary matrix, then S into S star is equals to I, that what we will have. And final very small and very important property is that whenever we are moving the port for a distance of beta L is nothing but the electrical length. Whenever the port is moved, not physically, it is electrically moved. Whenever it is electrically moved for an electrical distance of beta L, then the each and every reflection coefficient or the transmission coefficient which is related to that particular port will be multiplied with a coefficient of e power minus j beta L. Clearly remember this particular property, that whenever a port was moved for an electrical distance of beta L, then the reflection or transmission coefficients, that is nothing but the scattering coefficients which are related to that particular port, will be multiplied with this e power minus z beta L. These 5 are the properties you need to remember for deriving scattering matrix of any junction. That if you want to derive, so these are the properties you are supposed to remember. Using these properties, you can derive the constants. And one more point you are supposed to remember, the coefficients for this S matrix are complex. Always they may not be real, they are the complex quantities, because some phase differences also will be there between the input power and reflected power. Obviously they are the complex quantities. They may not be real always. Clearly remember that point. Now using these parameters for a two-port junction, just we will define few important losses or the few important formulae which will be useful for calculation of different types of losses. Now the first loss what we are going to observe is the insertion loss. Before that, just you once again recollect a two-port network. So let us take, this is the two-port network that what we have. For a two-port network, one will act as the input port, another will act as the output port. As per our assumption, the input which is applied at the port 1 is A1 and the reflected or the scattered one is B1, and the input which is applied to the port 1 is A2 and reflected from port 2 is B2. Right? Now what I do is just I'll give you another notation for this one for our simplification, that let us take, this is also called as the input power Pi. That for a port 1 we are applying the input, that's why I am denoting this one as Pi. And the return power from port 1, this is nothing but B1, this I am denoting as PR. Right? Here I am not applying any input at the port 2, so there will be no A2 for this particular concept. Only output will be there, that simply B2, which is nothing but P0. So this is to correlate the formula what we have with our scattering parameters or the scattering matrix. Just I am using this notation, the input power Pi is equals to A1. Actually this is not the power, right? This is a voltage. Later I will correlate. For some time just you remember like that. Pi corresponds to A1, PR corresponds to B1, P0 or the P output corresponds to B2. Right? Now with this simple one we will go to different losses. The first one what we are discussing is the insertion loss. How the insertion loss was defined? Insertion loss is nothing but simply how much power is inserted to port 2 when the power is applied at port 1. Insertion loss, how much power is inserted, process of insertion to port 2 when it is applied at port 1. So simply insertion loss, in short I am writing this one as IL. Insertion loss is equals to, you can take that one as P output divided by P input. Now what I want is, I want this one in decibels. Always the loss will be calculated in decibels, that will be most convenient for us. So what I do is, insertion loss in decibels, loss in dB, which is equals to minus 10 log, what is the basic formula that what we have? P0 divided by Pa. Now what I do is just I'll try to correlate this particular equation with the help of all these waves that what we have. Now which is equals to minus 10 log P output by Pi. Here we are using clearly powers, but the parameters what we have are the waves. Waves are nothing but the voltages. So power is directly proportional to voltage square. So easily you can observe that one. Easily you can use that particular relation here. So I'm writing this one as minus 10 log instead of P naught output power, I can write B2 square, right? So P naught can be written as B2 square divided by, instead of input power Pi, I can write A1 square. Once again I am saying that A and B are the wave strengths or field strength, they are not powers. They are the field strengths or voltages directly, you can take, no problem, right? So minus 10 log B2 square by A1 square, that what we have here, which is equals to 10 log, so I am reversing that one, this is A1 square by B2 square, A1 square by B2 square, I am rearranging this particular term, that 10 log 1 by, I am writing this one as B2 by A1 whole square. Now what is B2 by A1? B2 by A1 is the transmission coefficient from 2 to 1, right? So here clearly the transmission coefficient S21 we can write down here. So which is equals to 10 log 1 by S21 square. So simply this is the insertion loss for any particular 2-port device. So how much amount of power is transmitted from port 2 to 1, it's inserted, while it is inserting, how much amount we lost? This can be calculated using this particular formula, and if it is a symmetric junction, then S21 is equals to S12. So we can replace that one with S12 also. So this is a simple formula for insertion loss. Next we will discuss about return loss. Now we will discuss about return loss. So what is return loss? Simply how much amount of power was returned when some power is applied. So this is a very simple formula for that one. So return loss is equals to, taken as PR by P incident. How much amount of power was returned when some incident power is there. Now I require this one in decibels. That's why what I do is just I will apply minus 10 log PR by Pi to this one. So minus 10 log PR by Pi. Then what you will get is the same return loss in decibels. Now which is equals to, the same can be written as 10 log Pi by PR. As I said, the parameters what we have are the field strengths or voltages, but here what we are observing is the powers, or using is the powers. So directly relate them, which is equals to 10 log, how you can write down that one? Pi, instead of Pi you can write down A1 square, right? So A1 square divided by, what is PR? Instead of PR you can write down B1 square. So A1 square by B1 square. I am rearranging this equation, which implies 10 log 1 by B1 by A1 whole square. What is B1 by A1? The reflection coefficient at port 1. So this can be replaced with S11. So 10 log 1 by S11 square. Simply this particular parameter is said to be return loss. Clearly remember the word return. Return means how much amount of power is returned from the same port itself when the power is applied at port 1. So this is the relation between the return loss and scattering parameters. If you have powers, directly use it, no problem. But if you don't have powers and if you are interested to use scattering parameters, use this particular equation. This is one of the losses that what we have. Similarly, we can discuss about transmission loss or attenuation also. Now we will discuss about the transmission loss. So what is transmission loss? Simply it is the ratio of how much amount of output is observed to the transmitted. That actually in general case, if it is an ideal case, the observed is equals to the transmitted, then obviously you will get zero loss will be there. But in practical cases, definitely there will be some difference. So how much amount of power is observed to the how much amount of power transmitted from port 1 we require, right? So initially this can be written as P output divided by power transmitted. How much amount of power transmitted? That incident minus reflected. This is the incident, this is the reflected. If you subtract reflected from the incident, obviously what you will get is the transmitted. So P naught divided by Pi minus PR. This is the general formula for calculation of our transmission loss. How much amount of power will be lost while it is transmitting. We require this one in our decibels. So if I am converting this one into decibels, minus 10 log P naught divided by Pi minus PR, that what we have. Just rearranging that equation will give you 10 log Pi minus PR divided by P naught. Now this is the equation in terms of power. but we require the equation in terms of scattering parameters. So what I do is I'll replace this Pi with A1 square, PR with B1 square, P0 with B2 square. So this can be modified as 10 log Pi A1 square minus PR is nothing but B1 square divided by P output is nothing but B2 square. Simply it is this one. Now take just A1 common from both numerator and denominator, then this will be simplified, it becomes 10 log 1 minus B1 by A1 whole square divided by B2 by A1 whole square. Just I am taking A1 common from both numerator and denominator. Then what we will get here? 10 log 1 minus B1 by A1 is S11, B2 by A1 is S21. So simply it is 10 log 1 minus S11 square divided by S21 square. This is the equation which is useful for calculation of the transmission loss. While it is transmitting from port 1 to port 2, how much amount was lost? Clearly remember, for an ideal case this will be equals to 0. There will be no loss in our transmission line if it is an ideal case. That's why this is also called as attenuation factor. Directly you can call this one as attenuation factor, transmitted, observed, right? So this is this one, and the next loss that what we can observe is a reflection loss. How the reflection loss was defined? So basically how much amount of power was reflected and how much amount was lost, that can be observed using this reflection loss. Simply it is defined as the total transmitted power to the incident power. So what is the total transmitted power? As we discussed earlier, the total transmitted power is nothing but Pi minus PR, right? So Pi minus PR is the total transmitted power. Pi minus PR divided by what is the incident power? Incident power is Pi. But what we require is, we require this one in our decibels. So what I am doing is directly I am applying minus 10 log Pi minus PR divided by Pi. Now rearrange this equation, then what you will get is 10 log Pi divided by Pi minus PR, that what we will get here. Now I will try to write down all the powers in terms of our coefficients A and B. So which is nothing but 10 log Pi incident power is A1 square divided by Pi A1 square minus PR is B1 square. Now what you do is just you take a A1 common from both numerator and denominator, A1 square. Then what you will get here is 1 divided by 1 minus B1 by A1 whole square. This B1 by A1 is nothing but the reflection coefficient at port 1, that is S11. So which is equals to 10 log 1 divided by 1 minus S11 square. Simply this is to be the reflection loss. How much amount of power will be reflected or lost in the reflection form. So this is simple reflection loss. Like this we can define different losses and we can relate all those losses using our scattering parameters. So whenever it is given in terms of power, directly you can use this basic formula, or if the scattering parameters are given, you can use this one. So these scattering parameters are very important parameters. You need to remember how to formulate them, what are the properties of these scattering parameters, and using those scattering parameters how to calculate different losses in any transmission line system. This is a simple introduction of our transmission line coefficients and scattering parameters. Now we will discuss about a very simple concept called as bounce diagram in our transmission lines. So what is bounce diagram? Bounce diagram is nothing but a diagram which is useful for observation of the field intensity or the voltage at any given location in the transmission line or at any given instant of time. So this is called as bounce diagram. Now just I will tell you how to draw this bounce diagram by considering the reflection coefficients for both voltage and current. This is a very easy one. Just to observe what I am doing. Let us consider a transmission line is there which is extended from Z is equals to 0 to Z equals to L. That this is the length of the transmission line. This is not the transmission line. This is the length of the transmission line extended from Z equals to 0 to Z equals to L. Initially at a time t equals to 0, we are supposed to observe, so we are starting that one with a voltage wave. And assume that these two ends are not perfectly matched. Definitely some reflection coefficients will be there. At the load end, gamma L is the reflection coefficient. At generator end, gamma G is the reflection coefficient. Right? Now what you have to do is just you have to observe how this wave is traveling in this particular transmission line, and what I am assuming is this is a lossless line, that's why there will be no losses at all, there will be no attenuation factor at all, only reflection coefficients will be there, right? So at a time t is equals to 0, if the voltage is applied, obviously it will go to the load after some time. Let us take the time taken is t1. So at the time t1 it reaches our load, and the voltage strength or the field strength is just V0, right? Now after hitting the load, it returns or just takes a reflection towards the generator again, and it will reach the generator with this strength gamma L into V0. That the voltage which hits the load will be reflected, and the reflection coefficient will take place here. It's will takes a major role here, right? So gamma L into V0 is the now voltage which is observed in this particular path, right? And it is the generator end. Once again, this generator is not as perfectly matched. Since it is not perfectly matched, a reflection will be taking place and it reaches the load end again. Now what will be the time taken to reach our generator end? 2t1. T1 plus t1, the total is 2t1, and at 3t1 it reaches the load with the strength of gamma L V0 is the original one what we are observing here, multiplied with its reflection coefficient gamma z, right? So this is a voltage which is traveling for this particular load. Now after time t1 again it reaches the generator end like this with the voltage strength gamma L square, gamma L V0 gamma z multiplied with gamma L square gamma z V0 at time 41. Like this a bouncing diagram will be there from generator to load, load to generator, generator to load, load to generator. A bounce diagram will be there. Always this zigzag diagram will gives you the strength of our wave at different locations. If you want the strength of wave at this particular location, you can observe, and if you want the strength of a wave at a particular time, you can observe. So this particular diagram will gives you the strength of voltage or the field at different locations in the transmission line or at a given instant of time. The similar type of bounce diagram can be useful for observing the current also. So what is the major difference between the current reflection coefficient and voltage reflection coefficient? Just one is opposite to other, that they are 180 degrees out of phase. So what I do is just I draw the current reflection coefficients also here, the bounce diagram for currents. Let us take once again the same reflection transmission line I am considering. This transmission line is extended from Z equals to 0 to Z equals to L. Let us take the current reflection coefficient here is minus gamma z. The current reflection coefficient at the load end is minus gamma L. Initially I am applying I0. That the current what I am applying here is I0. This I0 is taken at a t is equals to 0. After some time, that is at a time t is equals to t1, the I0 as it is reaches to the load, right? It reaches the load. Now whenever it hits the load, it takes some reflection and reaches our generator again with minus gamma L I0 strength. Now the strength is minus gamma L into I0. So the time taken to travel up to this one is t1. So t1 plus t1 is 2t1. That's what we have here. Now it hits the generator end. Whenever it hits the generator end, it immediately takes the reflection because it is not perfectly matched. Now what is the strength that we will have here? Whenever it is taking a reflection from this one, minus gamma L I0 multiplied with minus gamma z, this reaches our load end at the time 3t1. Like this, whenever it hits the load end and the generator end, load end and generator end, it bounces, and what we will have is different field strengths or current strengths like this. This is called as a simply bounce diagram, which will be useful for observation of voltage and current at the transmission line.